So I'm very grateful for the chance to be included. Probably a lot of you could identify this white peak here, it's Mount Hood. So this is one way you can get to work at OHSU. The only thing that's a little bit deceptive about this picture is what's being left out, which is that you can see two other snow-capped volcanoes from this tram, Mount St. Helens and Mount Adams. Okay, another question. Does anyone, this is not me, does anyone know who this is besides John? So this is Brian Drucker. This is the guy that developed Gleevec in the 90s at OHSU. And he's the head of our cancer center and helped raise $1 billion for the new Cancer Institute. So it's a small city in a small place, but we have some things going on there of interest. And of course we have theory. So today I'm going to talk to you, probably going to spend half the time talking about theory, mostly in the first section. I'm going to talk briefly about a great passion of mine, weighted ensemble, but I'm going to spend maybe 40-ish% of the time talking about how some of this theory that we basically learned as we were learning to do weighted ensemble properly, and how it can be useful in understanding MSMs and improving them. So that's sort of the agenda for the day. And I think a lot of you have seen this picture before. We've seen various visualizations of this trajectory, but I think this is one of the scariest pictures you can see in our field, right? Because, you know, there's new phenomena that emerge after hundreds of microseconds in what should be the most boring protein that we might ever look at. So that's, you know, that's why we don't just do MD, most of the people in this room, but this is, I think, a nice way of thinking about it. So today we're going to be talking about the theory of trajectories. I just want to remind you that, that trajectories are what nature does, right? Nature doesn't calculate partition functions or free energies or anything like that. Right? Nature sets the rules of dynamics, and everything else is a consequence. We're free to try to interpret, categorize, or whatever we want, but this is what's fundamental. So we're going to work with trajectories. So, you know, most concretely, if this were 2 dimensions, this would be x and y positions, and we could follow them as a function of time. And in this theory section, we're going to assume we're omniscient, so we know all the history of these trajectories as well. We can go back in time, and I think it's for the people in this room, it's not a big deal if we generalize this to high dimensions. Of course, we're just going to be projecting things into 2 dimensions because, like Benoit, we're limited in what we can visualize. So this is going to be the fundamental object. The dynamics come from nature, from your computer, whatever. We don't need to worry about the details of that too much, except they're going to behave the way you think, and systems are going to be ergodic and stochastic and all that good stuff. So this is a picture that's a key starting point. It's an equilibrium ensemble of trajectories. Okay, so even though I'm showing, you know, a couple dozen trajectories in the same place, you should imagine that each of those is independent. Okay, it's an independent system, and for convenience, I'm showing it on this plane. Okay, and you know, we want to think of it pretty precisely. So the tips of the arrows are the present configuration of the system, and the tails are the history, and the good news is, again, that we're omniscient. So we can trace that back as far as we care to. And this is sort of where it all starts. Again, when I say these are independent, you should imagine they've been running for a very long time. And again, they could be simulations or it could be actual natural systems. Okay, so if we have this ensemble, we can, you know, kind of measure what any equilibrium quantity we want. Something simple, we can just draw these arbitrary states A and B, and we can count up the arrow tips in those states, and we'd have the equilibrium populations. We could make a histogram along our favorite coordinate and you know, take the log and get a potential mean force. So all that good stuff is in here. But there's more because we have trajectories, right? So we're running these dynamics. So we can do this very interesting construction that was first, it's sort of implicit in some work that Peter Bollweiss did, and then Eric and Aaron and Alex here also thought about these ideas. Basically that we can take our trajectories and we can classify them into 2 groups. Those that have most recently been in state A, again, which state A is arbitrary, but once we draw it, it's that group, versus those that have most recently been in state B. So again, we have, I'm showing the recent history, but you imagine tracing it back until it hits one of those states, okay? So each of these trajectories is one of two types. And it's not hard to see that this decomposition leads to two non-equilibrium steady states, okay, that exactly sum to equilibrium, if you will, right? Because when the red trajectories enter B, they turn black. And likewise, when the black ones enter A, they turn red, and it's equilibrium, right? So it's going to be an equal and opposite flow doing that, right? So this is interesting, sort of elegant, and let's see what we can do with this. So the first thing is we're going to focus, since we're basically everything that I'm going to be interested in today is to study a process moving in one direction. So we're going to say it's A to B, it could be B to A, but so the red trajectories. And I want to emphasize that sometimes mechanism is characterized in different ways, but really it's this ensemble that's the mechanism, right? Because there's no single state that characterizes it. There's no single path. It's really, the set of paths and the fractional populations of those paths, or if you will, the fluxes through those pathways. So that is the mechanism. We'll come back to that a little bit later. And just for convenience, some of you may, if you, I think I had a, let me see if I, no, okay. So another way we could think of this red and black decomposition is if you imagine tracing a very long trajectory through space, and you could cut it up into red and black parts, which is the way Eric and I wrote it down actually originally. But I also want to point out that, so if this is like an entry point to state A, there's going to be a couple of time scales that we want to keep our eyes on. One is the mean first passage time, or for one trajectory, it's just a first passage time. We don't know the mean yet. So it's from when it first enters to A to when it first enters B.
This meeting at Vertex.
Sorry, so sorry.
So, and then there's this shorter time scale that's essentially the event duration, which is from the last exit of A to the first entry of B. Okay, so and typically you expect this time scale should be much shorter than the first passage time. Doesn't have to be true, because they both they depend on how you draw the states, right? But that's generally true. So one thing that's very useful about this, maybe I should put on this mic. So, about this this particular the steady state, not this particular steady state, but any steady state actually. Yeah. Sorry. Okay. Sorry about that. So there's a relationship called the Hill relation, which 50% of people consider obvious and 50% of people don't believe, but it's true, and it's an exact relation between the probability flowing from state A to B per second and the mean first passage time. And so that's one way we can define a rate, is the inverse of this mean first passage time, and that's exactly equal to the probability flow into state B. I have a blog post on how you can see that is true. But the thing about it that we want to appreciate, and that's sort of tantalizing, is that if we could have a system in steady state, we would be able to estimate a long time scale from a short simulation of that steady state. Okay, because the probability flow into state B is going to exactly give us this inverse mean first passage time. So that's something else we'll keep our eye on. Okay, and this is the last kind of, well, I don't know if it's not the last base. It's another, there are a number of important things we need to understand. Okay, so now let's say we're going to discretize our space, okay? That means, so we've decomposed our equilibrium ensemble into the two steady states, the red and the black. So in each of these regions, microstates, mesostates, whatever you want to call it, there's going to be some of the red and some of the black. So I'm going to label the red alpha and the black beta. Okay, so the equilibrium population of each cell is the sum of those two. Okay, and that's kind of obvious. but something that's maybe interesting and maybe some of you haven't thought about is that if we could calculate the transition probability from I to j actually in three ways. Number one, we could just group all the trajectories together. And I'm going to call that the sort of equilibrium transition probability. So if we have that equilibrium ensemble, what's the probability to go from I to j in some interval of time? But furthermore, we could calculate it just from the alpha trajectories or just from the beta trajectories. And there's a relation between those two, which is pretty, I think, straightforward. It's just the weighted average of those two, where these are the same probabilities here. Okay? So the equilibrium rate is actually a sum of these two kind of non-equilibrium rates. And that's something that's very important because if we think about our first passage time, which depends on the flux in the direction from A to B, that means that if we want to study that in a discretized space, where I'm going to assume that state B basically consists of just a group of cells, okay, then I don't want to use just any of these rates. I need to use only the alpha ones. Okay, if I don't do that, I will make an error. Okay, so this relation is exact in a discretized space so long as you restrict yourself to the transition probabilities in the alpha subensemble. Okay, and the cool thing about it, I said it's exact. It's exact. So I didn't say it depends on how we define the states. It doesn't depend on the lag time or the discretization time along which we compute that transition probability. It's just exact. Okay, so that's a cool thing. All right, and actually, I say no. There's no Markov assumption. In fact, yeah, and there's no Markov assumption. Right, and it's because you get away from it because you're not using this Markov rate, which mixes the two kinds. Okay, so we're going to come back to that. So another way of thinking about that is that our underlying process, I'm always assuming, is going to be Markovian. I think that's fairly true to nature. Microscopically, meaning including all degrees of freedom. But if we want to project onto a subspace a coarse set of degrees of freedom, a discrete set of states, we lose that Markovian property. So if you haven't thought about that, you can think about it just in terms of a one-dimensional trajectory. You could calculate these rates from this underlying trajectory from going 2 to 3, 3 to 4, right? And you can do that. I mean, you can get the exact equilibrium rates. But if you put them together, those rates that you just calculated, and try to calculate the time to go from 1 to 4, you're going to make a mistake. You're going to think it's too fast. And why? Because when you mix the red and the black trajectories, you fail to account for the fact that all the red trajectories, when they go from 3 to 4, they had to start at 2, essentially, right? So that's harder. Takes longer. Not the same thing. Okay? This is intrinsic to discretization. Okay? And this is not, I didn't discover this. This is well known in the Markov modeling community. This is the whole reason why you adjust lag times, but I just want to put it in these different terms so you can see what's going on. Okay? And maybe to make a one simple example, I don't know. So if you imagine I have a simple process, simple diffusion, a flat potential, right? The equilibrium distribution is flat, right? But those red and black distributions will have this shape. Okay, so if you think about the probability within a given bin or a given cell, so the red is always going to be trailing, going to be higher back towards state A, right? And the opposite for B. So that's the difference. And this basically you can't. If you think about it, the way you calculate these rates is implicitly based on the distribution of starting points in cell I. So if you don't have that right, you can't get the rate right. If you do have it right, you will get the rate right. And the only way to get it right is to have it to follow this red distribution, which you won't do if you take the equilibrium mixture of them. And this is sort of equivalent to me saying it takes longer to come from the left because, just like that's why you have more probability back here. Okay? So that's sort of the basic picture of that stuff. So that's the main part of the theory. Now I'm going to kind of breeze through weighted ensemble and then get to Markov state model. I'm just excited about some of our new results. For those of you who don't know, weighted ensemble is just a way of orchestrating a set of trajectories. And you keep track of the weights. So it follows the unbiased time evolution of that ensemble. So if you're familiar with Fokker-Planck or Smoluchowski equations, it recapitulates that behavior. And there's some different nice features about it. It can be interfaced with many different packages. And of course, maybe not of course, but we keep that color information. We can stay in the red ensemble if we want to. Because we know we're tracking the full continuous trajectories. I just want to show you some recent data we have, which I'll say up front is good and bad, and I'll try to say both things. But this is an estimate of a folding rate for NTL9 in implicit solvent starting from a single structure. Okay? And the thing that I like about this is that I think that we've really nailed the value that I don't know that anyone's been able to do before in a rigorous way at room temperature, even in implicit solvent. And we see that the rate is kind of faster than the experimental. And whatever, that's just the way the model is. But now we know it. You'll also see these light gray lines are different runs. There's a lot of variance. In fact, if we make the system a little harder by putting it in a higher friction, the variance is even bigger. It's a little bit closer to the experimental value, but it's still faster, maybe by an order of magnitude. And this arguably should be sampled a little more. We're working on it. These timescales that we're estimating here are about 100 microseconds. And it's taking us about 100 microseconds to do it. But of course, we're getting the ensemble. We're getting an error bar. We're getting all that. So you could say, oh that's interesting. Of course, we didn't know how long it would take, right? So you could just try to run 1MD and wait and keep your fingers crossed. But so here you do it in parallel and you're getting statistics. I think it's much preferable. But here's an example I think is a little more striking. Here we're able to measure about a 10-second time scale. And so you can see measuring really the flux just using that Hill relation that's going into the state. Again, I don't have a lot of time to discuss it because I want to get to the other stuff. I tried to have all the caveats here. Particular, keep your eye on the issue of what's the unfolded ensemble. Intrinsic ambiguities there that I don't have time to go into. Talk to me later. So, and by the way, if anyone's interested in weighted ensemble, we are having a workshop and registration is closing soon. You can just find it on the website. OK, let me get to the Markov state model stuff. So I wanted to, based on some of our experience using that type of theory, we started to wonder whether these issues were important in all Markov state models as they're traditionally made. How accurate are they? What are the issues with lag time and so forth? And when I went back in the literature, I didn't see that there was a very careful comparison to LongMD. There were comparisons of different sorts, but not the type that I like to do, which I'll explain to you. And furthermore, if we know this theory, how can we use it since it's exact, right? At least for the mean first passage time, how can we use it maybe to improve Markov state models? So that's sort of the program. And we're going to do it using the Shaw folding trajectories, which I think are probably among the only well-sampled MD trajectories in existence. So they're a good thing to look at. And what we're going to do is use the traditional Markov models and then also use Markov models that are modified for that labeling, alpha and beta, the black versus red. Okay? And that's what I'm going to talk to you about. So to some extent, we're going to use the standard MSM procedures, which have been discussed multiple times. What's going to be a little different here is we wanted to make the study as objective as possible. And by the way, did I did I say this is joint work with John Chodera and Frank Noé? Because I'm happy to make my own Markov models, but they're never going to be good. So Frank's group made them. I'll show you that. We wanted to make states that weren't chosen so subjectively, so we did an automated clustering procedure, which I don't have time really to get into, to choose basically the folded and unfolded state definitions. And then instead of focusing on implied timescales, we're going to look at specific timescales for the folded to unfolded transition. And I'll say a little bit about that right here, which is that namely, when you measure implied timescales, you don't know what process you're really getting there. And I've heard certainly anecdotal cases of when people have found timescales that didn't correspond to the process they were interested in. So here again, maybe you're interested in the red-green transition, but the purple thing is the slowest, right? So that we don't want to have that problem. We did hierarchical kinetic clustering, nothing too fancy to get these states. I won't go into it. But basically what we did, we took the trajectories, a uniform data set, we put it the regular Markov state models. We used the same exact microstates and built this other kind of model where we kept track. We separated the two types of rates, basically. That's all we did. And we also did another little trick, which we said, well, maybe David Shaw has trajectories that have 36 transitions. Most of us don't. What if you only have a limited amount of history? So we built that into our models. Now it's approximate. And the way that we did it, basically, so if you think about this trajectory, this little segment goes all the way back, and we can say its color, if you will, that it's red. Some of them may not, in which case we basically just we assign it a fake history chosen from a Markov model. So it ends up being equivalent. If we don't know the history, we say it's like a Markov model. If we do know it, we do it that way. So we went through, I want to say, the usual validation, but actually this is much more stringent, I think, than is usually done. These models were built by Chris and Simon from Frank's group. And I want to show you something I don't think you often see, which is the implied timescales put on a linear scale. Because I invite you to take your standard plot and plot it on a linear scale. And I think you may or may not like what you see. But when you do it on a linear scale, I wasn't sure that they would see it leveling off. Frank said, of course we'll see it. Anyway, he's right. But pay attention to when it levels off. Okay, that's about 200 nanoseconds. Okay, so this is a case, we have a lot of data, so we can really do this thoroughly. You get the implied timescales leveling off at 200 nanoseconds. The regular CK tests look good. And so anyway, the people who know this best did the validation. And I think, I just want to say too quickly, a little bit more theory. The mean first passage time depends on the time discretization, or you can think of it as lag time. Nothing to do with Markov state models. It's intrinsically true. If I have a long molecular dynamics trajectory and I only look at it every so many frames, I may or may not see the first point of entry when I do it, right? So depending on how I'm discretizing, that's going to affect the mean first passage time. And that's something that we account for when we look at this. And again, the first passage time depends on the states, maybe too sensitively. That's another issue we're looking into. But so generically, as you increase this discretization time, it's going to look like this. It's going to increase monotonically because you can only miss events. It may look like this and shoot off into basically trivial behavior where you're beyond even the mean first passage time. It's not kinetic information. If things, ideally, things would look more like this, where there was kind of a plateau, like a golden region of lag times, if our states are well defined, where it's kind of insensitive to the lag time. That's sort of what we would like to see if we did a good job choosing states. But I want to point out, some systems you may have this. Some systems, it may not be that your states are poor. It may be that it just doesn't exist in that system. It may not have any two-state character. There may not be deep basin system. But that's all for regular MD. Here's the data. Okay. So there's a few things on this. So first of all, I'm showing you the mean first passage time calculated in multiple different ways, from molecular dynamics, from the Markov state models that have been carefully validated, and then from these sort of history or color-informed Markov models. Okay, and note the scales. This is the mean first passage time on a log scale, and also this is a log scale as well. So let me jump to the good news about Markov models is if you go to the lag time, that's self-consistently predicted to be Markovian, which is about 200 nanoseconds, and what you find, the green bar is the confidence interval from MD, which indeed increases monotonically as promised, right? So like that would be about, so in this case it's about 200. You'll see that it agrees with molecular dynamics, right? But below that it doesn't agree. So there's something in there, there's some part of the magic is working. On the other hand, maybe this one has a little bit of a plateau, but that lag time is out here, maybe a little bit past it, maybe it's within it. You'll still get numerically a reasonable answer, but it's perhaps not ideal. Maybe you'd like to be in the sweet spot. On the other hand, when you include those history labels about which subensemble, and you include all the history information, you get the answer exactly right, and shouldn't be surprising because the theory's exact. But you can get away with even just a little bit of history, and that's the dashed lines is when we use on order, let's see if I can read it, 10 nanoseconds or 100 nanoseconds. In other words, we pretend we haven't seen more than that in history. You can still do quite well in terms of doing these first passage times. And I'll show you, this is just for one of 4 systems, and they basically all look like this with some variation, which we can discuss later. I don't have time. So again, the message is the MSMs match the molecular dynamics at the self-consistent lag time, but it's a pretty long lag time. On the other hand, if you include the history, you're good to go at any lag time. And I see that I'm running out of time, and I'll just mention, from the MD, this event duration time, okay, it's only on the order in most cases of about 10 nanoseconds. It does depend on the state definitions. So when your ideal lag time is 200 nanoseconds for the Markov state model, you don't have really the resolution to look at mechanism. Okay, so think about that. This is a system where we can really tell, where we really have enough data to tell. We can tell that you shouldn't be looking at mechanism with the Markov state models. On the other hand, you can do it when you have the history because you can use any lag time. And when we compare using a histogramming technique that I don't have time to explain, but we just can build a histogram of mechanisms. We compare well with the MD trajectories. So I'll stop there and just remind you that your data probably isn't like the data that we had here. So this was kind of a unique opportunity to do this really carefully, and I'm very grateful to Frank and John for helping with this. And this guy, Ernesto, was kind of the one who did most of the heavy lifting and getting things done. And as I mentioned, Chris and Simon built the models. Thanks.
There's time for a couple questions.
By including the history, you definitely need more data to calculate the transition matrix, right?
Yes. So he's asking if we include history, do we need more trajectories? I mean, in principle, you have twice as many rates you're calculating. So
what is your general advice on how to choose the number of history?
I don't know if I'm in a position to have general advice yet. But what we see is that histories in the tens of nanoseconds. I would say I haven't seen a case where we've needed more than 100 nanoseconds. But we haven't seen everything. Yeah.
So folding, unfolding, or binding, unbinding. There's a lot of two-state systems out there that this is directly, I guess, applicable to. If there's multiple stable states in a system, can you just extend this to have more colors?
Yeah, you can have more colors, and then you have so if you have 3 colors, you'll have 3 times as many rate constants. Yeah, but yes, it's straightforward.
Good. It's a very, very nice talk. It was nice to see your points sort of summarized in this more formal setting. So you don't really show error bars on either the history-based predictions or the Markov state models, and these error bars are, so they are known, even if you include them, they are known to be underestimated because you have an over-parameterization in the Markov state models. And I guess this problem is even larger when you're working with these history-based models because you have even more parameters. So how do you think that this is influencing the overall sort of, how big of a problem is this? For instance, like if you look at hidden Markov models, we know that they are sort of condensing the information into sort of a smaller parameterization ideally, and they actually reproduce the dynamics much better. So what are your thoughts on these?
Yeah, well, so certainly it's an important issue, and yeah, we're still finalizing this. So it's an excellent point that we should include the uncertainty for the models, which isn't here. But the the theory part is still holds. There's an intrinsic bias when you're at these shorter lag times that you've thrown away the information, you can't get it back. So you must use some kind of history, as far as I understand it. What will happen when we more carefully account for the error, I don't want to say because I haven't seen it.
Yeah, that's the point about the hidden Markov models.
So again, so I haven't worked with them. I understand you to say that you get away with fewer states, you have fewer parameters, so that would be good. But actually, fewer states is actually only going to exacerbate the history problem from a theory point of view. So I don't know. We'd have to look at the data together to see.
Right.
So have you, I mean, with these simulations, you have the MSM, so you looked into like the highest flux paths from the MSM between these two sets of states, and I'm curious if the time scale is wrong, is the mechanism, is it also finding mechanisms?
So Greg asked me this question before, actually, and he motivated a lot of what we've done. I don't know if he's forgotten or just pretended, but so yeah. So just to repeat what I said maybe more clearly, and at least I think John and I agree, and I think Frank agrees as well, that when your lag time that is basically selected from the validation is on the order of 200 nanoseconds, you can't go ahead and look at a process that occurs below.
But I meant with the shorter lag times, like if you.
So if we now go ahead and.
Go to 20 nanoseconds.
So we've done that. Yeah, the fluxes. So okay, we've done our version of that. So we have a way of, again, classifying these trajectories, because I think there's issues with the flux analysis that I don't like because paths can't cross, but real trajectories will always cross flux paths. So we have a way of histogramming regular trajectories. Yeah, the MSMs don't, the mechanisms are different. And basically, if you think about it, an MSM is more permissive, right? Because you don't care where you've come from, you're happy to go wherever, whereas in some sense, the history is going to narrow down that distribution of what you might do. So that's a short.